Welcome to This Explainer. Look, if you've ever felt completely intimidated by complex database queries, you are absolutely in the right place. Today, we're going to totally demystify database architecture. We're going to shift your mental model away from those abstract lines of code and move toward clear visual connections. We'll be looking at exactly how scattered data fits together, piece by piece. Here is our roadmap for today. We'll kick things off with why we join tables, look at the anatomy of a join, and then break down inner joins, directional joins, and full joins before wrapping up with some fantastic pro tips. Think of each join we cover as a specialized tool designed to solve a very specific data problem. All right, part 1, why we join tables. Let's dive right into the foundational question of why we even need to recombine fragmented data in the first place. So how do we actually go about combining tables? Well, in the real world, databases are highly organized, which ironically means your data is usually scattered across multiple places. You might have one table just for your customers, another entirely separate one for their orders, and maybe even a third for shipping addresses. When you want to see the whole picture, you have to decide exactly how to stick those puzzle pieces back together. And this brings us to a really brilliant distinction. You basically have two choices when combining data. You can combine rows, or you can combine columns. If you use set operators, like a union, you're stacking rows vertically. It just makes your table longer, kind of like adding more names to the bottom of a guest list. But joins? Joins are a totally different beast. They place columns side by side. You aren't adding more people, you're adding more information about the people you already have, creating a much wider, richer table. In practice, we primarily use these side-by-side joins for 3 specific tasks. First, obviously, to recombine that fragmented data into one big, cohesive picture. Second, for data enrichment, like using a lookup table to quickly attach country codes to a customer list. And third, to simply check if data exists, like, say, filtering your view to only show customers who actually placed an order this month. Moving on to part 2, the anatomy of a join. Before we start actually mashing tables together, we really need to understand the underlying mechanism that makes it possible. So, the absolute most crucial point is this, the key column. You must have a matching key, like a customer ID for instance, to connect the dots between your left table and your right table. Without this common identifier acting as a bridge, the database literally has no idea which order belongs to which customer. It's the absolute linchpin of the whole operation. If you think of SQL as a highly organized, maybe slightly obsessive worker, this is exactly how it operates. It reads sequentially, it starts at the left table, looks at the very first ID, and then actively searches the right table for a match. It is only going to output that combined wider row of data if that specific condition is fulfilled. Which brings us to part 3, inner joins. Let's see how this sequential worker logic builds into our very first and probably most classical method. The inner join is strict, really strict. It returns only the matching rows from both tables. Any unmatching data on either side, it's completely ignored and thrown right out of your final result. And because it only cares about perfect overlap, the order of your tables doesn't matter one bit. Table A joined to Table B will give you the exact same result as Table B joined to Table A. Notice how this plays out in the combined output. SQL happily matched customer ID 1 and customer ID 2. It neatly combined the customer names from the left, Maria and John, with their exact order IDs and sales data from the right. If there was, say, a customer ID 3 who hadn't bought anything, they wouldn't be anywhere near this list. An inner join demands a perfect match. All right, part 4, directional joins, specifically left and right. Because what happens when we want to keep all our data from one specific table, regardless of whether there's a match? Well, this is exactly where the spatial order of your tables in your query becomes incredibly important. With a left join or a right join, one table essentially becomes the priority master source and the other acts as secondary lookup data. A left join guarantees you are going to see every single row from your left table, even if the right table has absolutely nothing to offer. What's really fascinating here is how SQL handles Martin and Peter in a left join. Because the customer table is prioritized on the left, SQL immediately outputs them. But when it searches the orders table on the right and finds a whole lot of nothing, it doesn't delete them like an inner join would. Instead, it visually cements that gap with the word null. It's basically SQL's way of shrugging and saying, hey, I kept the customer, but the order data is totally unknown. Here's a really fun little secret from our source material. Because left and right joins are literally just logical mirrors of each other, The instructor admits he hasn't actually written a right join in 10 years. Seriously? No way. Instead of confusing himself by constantly changing the join type, he sticks exclusively to the left join and just swaps the physical order of the tables in his code. It achieves the exact same result with far less mental gymnastics. Part 5. Full of joins. Sometimes you just don't want to play favorites. You want absolutely everything combined. The full join is the ultimate combination tool. Just like the inner join, table order doesn't matter here. But instead of looking for strict overlap, it ensures zero data is left behind from either table. It grabs everything from the left, everything from the right, matches them up in the middle wherever it possibly can, and then just aggressively injects nulls into all the blank spaces. And here is exactly what that controlled chaos looks like. In this output, you see Martin on the left with nulls on the right because he didn't order anything. But then look right below it. You have an order ID of 104 and sales of $100 on the right, but complete nulls on the left. This means we literally have a ghost order in our system that lacks any associated customer record. A full join is amazing because it exposes all the gaps in your database simultaneously. Finally, Part 6. Pro tips for SQL Joins. To wrap up this explainer, let's quickly go over some insider best practices for writing clean, professional database queries. First off, always explicitly type out inner join instead of just join. It makes sure the next person reading your code knows exactly what you intended. Second, prevent SQL from getting confused by defining the table for identical column names, so write customers.id. But since writing out full table names gets super tedious, our third tip is a real game changer: use table aliases. Just use a simple C for customers and an O for orders. It's a fantastic trick that saves massive amounts of time and makes your connections visually obvious. So think about it. Understanding how these spatial table connections work gives you incredible power over your data. By mastering just the left join, the inner join, and some clean table aliases, you can solve nearly any data fragmentation problem out there. It leaves us to wonder, now that you have this visual framework, how will you recombine your own scattered information next? Thanks so much for joining me for this explainer, and have fun experimenting with your data.